So now we're going to finish off this first part with exponential decays. For exponential decay situations, well, you'll see there'll be radioactive decay or half-life, but again, I'm actually just going to kind of dive right into the questions, and we're going to look at them, and then I'll explain them as we go through. So the half-life of sodium-24 is 14.9 hours. A hospital buys a 40 milligram sample of sodium-24. Now, when we're looking at half-life, what half-life means is the amount of time that's required for half of it to disappear is 14.9 hours. So if you started with 100 grams, after 14.9 hours, you'd have 50 grams. How many milligrams to the nearest tenth of sodium-24 will remain after 48 hours? So again, I need to build my formula. I'm going to go A equals, we're starting with that 40 milligrams, and then, since it's half-life, half it is constantly disappearing, and my time is going to be divided by that 14.9. So then, I'm going to pop the 48 hours into this, so I get 1 over 2, and then I go 48 divided by 14.9. We grab out our calculators and we punch this bad boy in, and we get 40 multiplied by 1 over 2 to the power 48 divided by 14.9. And this will tell us that we'll have approximately 4.29 milligrams left after 48 hours. After how long will only 2.5 milligrams remain? So this is going to be another one of those situations where we take this and we pop it into our graphing calculators. Well, let's build the formula first. So we want to know how long it'll be for 2.5 to remain, so that means on my left-hand side I'm going to have the 2.5. Then I'm going to pop my original equation into this. 40 multiplied by 1 over 2 to the power x all over 14.9. Now again, what we're going to do here is we're going to handle this as we've handled the questions previous to this. All that I'm going to do is I'm going to pop this into the calculator. So I'll say y1 equals 2.5 and y2 would equal 40 to multiplied by 1 over 2 to the x all over 14.9. Now when we pop this into our graphing calculator, one of the things that you guys will notice is it'll switch up ever so slightly. And what I mean when I say it'll switch up ever so slightly is the graph that you're going to get, again, depending on window settings, will show that we have that exponential decay there instead of the exponential growth that we had before. I'm just going to quickly erase that line that I drew in there, and I'm going to draw it in a bit better. So it'll show kind of that the answer will lie a bit further. So we go second trace, and then our classic intersect, enter, enter, enter. And this will give us that it will take, well, around 59.6 hours. So after 59.6 hours, only 2.5 milligrams will remain. To determine whether a person has a thyroid deficiency, radioactive iodine with a half-life of 8.2 days is injected into the bloodstream. A healthy thyroid gland absorbs all the radioactivity. Determine an exponential function that models the amount of radioactive iodine that should be present after any number of days. So we give this a try. We have that it has a half-life of 8.2 days. Now, one thing that you guys will notice right here is it hasn't given us an initial value. So since it hasn't given us an initial value, I'm just going to keep a 1 in there. And I'm going to put the 1 in there. You could also use 100, meaning 100%. As a decimal, we know 100% is 1, so I'm going to leave it as 1. Then it's a half-life, so it's 1 over 2, and the half-life is every 8.2 days, so I'm just going to go T over 8.2. Now scrolling down, After how long should only 25% of the radioactive iodine be present in the thyroid gland of a healthy person? So going back, I have that formula that I used before. Now, since we have that 25%, there's two ways that I could handle this, and I could keep that one in the front. No, you don't need to write it out again, or write the one out. But I'm going to, just to show what's going on. Or I could modify this, and I could put everything in terms of the percentages. So it doesn't really matter which one of these two that I choose. Both of them will give me the exact same answer. Realistically, it's more of just what you're comfortable putting into your calculator, and it comes down to how comfortable you are changing the window settings up. So we put this in, and then we get the t, or rather the x over 8.2 when we punch it into the calculator. And we again do our classic graph, where we get a graph. That'll look somewhat reminiscent of this. We go second trace, and then we go to our intersect. We go enter, enter, enter. And sorry, I'm just having a little quick technical difficulty right here. So again, we go second trace, and then we go enter, enter, enter. And it comes up that my answer is x equals 16.4. So it'll take about 16.4 days. Okay. The intensity of the light below the surface of a particular lake is reduced by 4% for every meter below the surface. Write an exponential function that models the intensity of the light at any depth below the surface. So now what we have happening is we're reducing by 4%. I'm going to go back to my t-shirt analogy that I had before, and let's say you're buying a really expensive t-shirt. That's $100. But magically, that $100 is now 5% off. So I could multiply that by the 5%, get the $5, and then go 100 minus 5 equals 95. So that would leave me with a total cost of $95. What I could also do is kind of the same thing I did before, but instead of adding, I could subtract. So I go 100 multiplied by, sorry, not 100, by 1, which would mean the 100%, and I could minus that 0.05. This would give me 100 multiplied by 0.95, which would equal the 95 that I'm looking for from before. So when we're looking at decay, this number that's going to go on the inside, we could also look at this as being what remains. So in this case, 95% of the value remains. So we want to write an exponential function that models the intensity. Well, again, we're going to start with that 1 to represent the 100%. Then, on the inside, I'm going 1 minus that 4%, or 1 minus that 0.04. Now, it's for every meter before the surface, below the surface, so instead of putting the time up there, I'm just going to put a distance, and since it's straight up, we're good. So now we get that it's going to be multiplied by 0.96 all to the power d, where that d represents the distance. Again, we're labeling variables here, so we do get a bit of leeway how we're going to do that. What percent of the original intensity of the light remains 10 meters below the surface? So we go A equals 0.96, and then that's going to be to the power 10. Which will give us approximately 0.66, or approximately 66% of the light will remain. How far below the surface does the light have to travel for its intensity to be 30% of the surface intensity? Again, I want to remind you guys, you could do this by multiplying everything by a factor of 100, but I'm just going to keep it in decimals in this case. So I go 0.3 is going to equal 1 multiplied by 0.96 all to the power x. So again, we punch this into our graphing calculators and we find what the intersection is going to be of these two graphs. Going over those steps again, we go second trace, enter, enter, enter. So I go second trace, intersect, enter, enter, enter. And this gives me that the x is approximately 29.5 meters. So it'll take about 29.5 meters, make that 9 a little better, to get 30% of the surface intensity. We're almost done here, guys. An average new car depreciates 15% in value each year. How long will it take for a new $40,000 car to depreciate down to $10,000 in value? My starting value is $40,000. And then we're depreciating by 15%. So I'm going to get 1 minus that 0.15, and that's every year. So I'm just going to put it straight up as being t right there. On my other side, I'm going to have the 10,000. Now again, I could divide both sides by the 40,000 and have 0.25 on my left-hand side. That is perfectly fine. It just really does depend on your familiarity with graphing calculators. But we get 10,000 equals 40,000 multiplied by 0.85 to the power t. Or if you wanted to divide that 40,000 by both sides, we get 0.25 equals 0.85 all to the power t. Again, we quickly punch this into our calculator. We graph it y1, y2, and we look for the intersection point between them. So I go second trace, intersect, enter, 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 and we get that the time will be approximately 8.5 years. As you guys can see, there's a homework assignment posted below, and I'll write the homework assignment on this lesson. I hope you guys have all enjoyed the first part of exponentials. The next two parts actually go quite a bit quicker than this first part. Have a great day, guys.